Welcome, everyone, to the Hall of Halls. And we're going to welcome our first speaker, the third Alice of presenter of S2P, son of Jacob, Alex Jacobson.
Thank you, Stephanie. I'm here to present progressive convex hull simplification. So convex hulls are, by definition, the tightest convex shape that we can fit around an input object, even if the input object isn't convex. So we can kind of line up a bunch of different convex containment objects, starting with a bounding sphere, to a bounding capsule, to a bounding cube, to an oriented bounding box, to k-dops, where we fit a given set of planes, all the way down to the convex hull being the tightest convex object. We can divide up the shape and put lots of little convex hulls on top of the shape. This is often called a convex decomposition or approximate convex decomposition. But of course, the whole thing is no longer convex. So we're going to focus on just the core problem of finding convex containment objects. And there's a big gap you can see between something like k-dops and the exact convex hull of a shape. And that's where this paper fits in. We're going to try to find something that's very tight, like the convex hull, but has low complexity, like the other shapes that I have on here. Hulls are really useful as acceleration data structures because they're conservative. So if we want to find out if rays intersect a complicated object like this dragon, we could first put it in a containment object like a simplified convex hull, check if the rays hit the hull, and if they don't, discard them, because they definitely don't intersect the dragon. Same thing for collision detection. So if we have two crabs that are fighting each other and we want to find out if they intersect each other, we can first check their convex hulls and see if they intersect, then the crabs themselves might intersect. If they don't intersect, then the crabs definitely don't. Convex hulls are nice because those checks are really cheap. So for example, if we want to check if two convex polyhedra overlap, we can reduce that to a very simple linear problem. To do that, I'll also introduce some notation, so this will be nice. So let's start with a single convex shape. Convex shape, we can represent, discrete one, we can represent with, sorry, my phone is ringing. OK, good. We can represent it with a set of half spaces aligned with each of the planes or edges in a 2D example. Each of these half spaces we can represent by the normal direction and then the offset from the origin. So 3 numbers or 4 numbers in 3D. And then if we want to check if some point x is inside of our convex hull, we can just check an inequality with each of the plane equations. We can just check if its dot product with the normal plus this offset is less than 0. Now if we want to check if two convex shapes overlap each other, we just need to prove whether or not such a point x exists across all of the faces that we have. So write down all the inequalities across all of the faces of the two objects, and then find whether or not there's this point x. This is a linear program, and you can solve it in linear time with respect to the total number of faces that you have. What's kind of nice here is we didn't need to talk about vertex positions at all. We only need the half-space representations, the plane equations. The unfortunate thing is that if we take exact convex hulls, this scales with worst case linear complexity in the input. Obviously, if the input is a really complex convex shape, its convex hull is just itself. In practice, it's like better than this, but still bad. So if you take all the 133 models from the 3D scans data set, and you count the number of faces on the input meshes, then you'd get this pink histogram over here. And if you count the number of faces on their convex hulls, you get this green histogram. So it's like definitely a lot less, but it's still like, I don't know, about like a factor of 100 or maybe 1,000 in terms of the input number of faces. The good news is you can remove almost all of this complexity without changing the shape of the convex hull. So here, this is like a preview of a result. Here I'm showing the owl, its exact convex hull, and then like progressively removing a lot of the faces. And we can see that the shape doesn't really change and its volume doesn't really change until the very end, until we're removing like down to like 18, 12, 6 faces. It made it hard to show results for this paper because like mostly the 2 images just look the same. So like a lot of the results are like extremely aggressive simplifications, mostly to show that there's something different happening. So the goal for this work is to take as input an exact convex hull, represented as a list of faces, and reduce it to a potentially very small number of faces with minimal change to the shape. We can measure that change to the shape in a variety of different ways. I'll get into that later. But here it's measured in terms of volume change. Compared to some other works, this work, for example, removes vertices and tries to keep a triangle mesh that contains the shape, but doesn't do quite as well in terms of the volume preservation. And this standard technique for bounding volume hierarchies fixes the plane orientations ahead of time and just makes those as close as possible to the shape. And this does very poorly in terms of volume preservation. The way that we're going to do this is going to feel very natural to people from computer graphics or geometry processing. We're going to take standard ideas from triangle mesh simplification, and we're going to do it on the faces of the convex hull. So we're going to greedily remove faces of the convex hull, prioritizing smallest increase of whatever change that we're measuring, if it's volume or area. So it's like QSlim or progressive meshes, but with a little bit of a twist in how we do it. We're removing faces because if we remove a face, we trivially contain the input, right? So if I drop this red face of our 2D example, we'll always contain the original white shape. We'll get some new volume that's like revealed from extending those faces, neighboring faces beyond it. And that's the thing that we're going to measure every time we remove a face. But fortunately, this change to the shape is local, just like mesh decimation is a local operation, and that's going to lead to an n log n algorithm. Now, so far I've showed just 2D figures. In 3D, it's a bit more complicated. So if I want to remove this red face that has these vertices next to it, the faces in general will be polygonal. So we'll have many different polygonal faces as neighbors to this. And when I remove the red face, they're going to come like crashing into each other and create new vertices and new edges. And if we tried to do this explicitly, we'd have to track all these new things and be careful about numerics and making sure that we have the correct topology. That's not how we're going to do this. So we're definitely not going to do explicit computation of intersections of planes and try to add them on top of the shape. The key idea, it was nice Justin said like dualize everything. So that's the idea in this talk too. So the key insight is that we're going to work in the dual space. So in the primal space, that's where we actually think of this thing as the convex hull. We have vertices of the convex hull, and we have planes. And before, remember, we represent the plane with the normal. To convert this shape into the dual representation, all the planes are going to become vertices, and all the vertices are going to become planes, and edges become other edges in the right way for 3D. And you can think of the new vertex positions as basically kind of taking the normals and turning those into vertex positions, and then going back the other direction, you can create the original vertices by taking normals of the dual faces and treating those as vertices in the primal spaces. By the way, this is how most libraries implement half-space intersections. So if you had a bunch of half spaces and you wanted to compute the polyhedron that they possibly enclose, most libraries first convert all of your half-space representations to dual vertices, run a standard convex hull algorithm there, and convert it back. So this is definitely not new. The cool thing is that maybe not everything, most things that you want stay convex, which is really nice. So when we had a convex hull in the primal space, this is also a convex hull in the dual space. What's kind of cool here is that in the primal space, we had all these planes crashing into each other. Most planes will intersect at a single point. And since those points become faces in the dual space, then, sorry, I want to say this better. Most of the time in the primal space, we have just 3 planes agreeing on a point, right? If they're in general position, we can think of them as like randomly oriented. You're not going to have 4 planes intersecting at a point. You just have 3. That's nice because in the dual space, that means their corresponding dual face will be a triangle. We can just represent everything with a triangle mesh. So primal faces removed in the primal hull corresponds to removing a vertex in the dual hull. And that's something that we're just like ready to do with our data structures. Great. So there's 2 aspects to removing a dual vertex. There's a topology change and a geometry change. I'll first talk about the topology change. So if I want to remove this vertex here, I will, I'll delete it. I'll have a one ring of dual vertices around it, and I need to re-triangulate those. Their topology is determined by the geometry. We need to connect the edges here so that each of the edges is convex. We could do that by running a tiny little convex hull problem on the M neighbors that we have, or we could do a cheaper thing, which is just like trivially triangulate them and then just like flip edges until everybody's convex. And when the problem's really small, that like dumb M squared algorithm is much faster than like invoking a standard convex hull algorithm. So that's what I do. I just flip edges. What's kind of nice here is that we didn't rely on any geometry constructions. We only relied on geometry predicates. So we need to know if an edge is convex, and you can reduce that to an orient 3D test, which is like a standard robust predicate, which is kind of nice. And then this should probably say not geometry change, but like geometry measure. Like how do we measure whether or not this was an expensive change to our primal shape or whether it was a really cheap one, and we should definitely do it. And the idea is we're going to take these two meshes and we're going to glue them together, the before and after. Now we have like a little cap thing in the dual space, and we're going to transport it back to the primal space like we did before. So all the vertices become faces and all the faces become vertices. And now we have a definitely convex cap in the primal space, and we can measure its volume, we can measure its surface area, we can measure its mean width, which is an interesting quantity for collision detection. And then that becomes the cost of removing that vertex. So we have the update to the triangulation, and we have a cost for every local operation, and that's pretty much it. Then it's just putting it in a big loop and taking off the cheapest ones one at a time. So the structure of the entire algorithm looks like this. There's a bit of pre-processing. So if the input is a non-convex shape, we're first going to compute its exact primal convex hull, convert all those primal faces into dual vertices. It's helpful to remove near duplicate faces here. You don't necessarily have to if you use exact libraries like Seagull to do the arithmetic, but if you don't want to do that, you could just like zap the ones that are close to each other. And remember, like two dual vertices that aren't really close to each other corresponds to two faces that are like essentially coplanar. So this is not really cheating or making it easier. It's just taking off things that should be eliminated anyway. Then we triangulate that thing. So I run convex hull algorithm once on all those vertices in the dual space. That gives us a triangle mesh. We measure, like basically pretend to do each vertex removal and put that in a big queue, measuring each one, and then start processing them. Every time I actually do a dual vertex removal, I need to update the cost of my neighbors because the triangulation has changed. So I need to loop over my neighbors and say, like, now pretend to remove that and compute what would be the cost of removing that and put it back into the big priority queue. If we do some like rough accounting on what the asymptotics looks like, the whole thing adds up to n log n expected performance. Let's see some benchmarking. So, okay, this is like just starting with like, what does that pre-processing look like? So running convex hull is already an n log n worst case algorithm in 3D. So this is saying for the number of faces in the output on the convex hull, how long did it take to create that thing over this big data set? And the fact that it's like not perfectly along the line shows that this convex hull algorithms are in some sense like not very output bound in terms of their complexity. It's not that interesting, but they're like mostly scaling linearly. Once we have that exact convex hull, then we can run this simplification algorithm, and we're seeing like really tight near linear performance, which is expected. Cool. All right, let's see if this demo works. This is a demo. There's not a lot to show, but I implemented and I want to show it off. So this is the convex hull of this shape, and I can like animate it and show it like peeling off. I think we can go farther. Yeah, I don't know. Oh no, I'm just like watching it myself. I thought it would be mirroring. Okay, I'll have to turn around. It'll be easier. Yeah, so this is the convex hull of this thing. And then I can animate it, peeling it one by one, or actually a bunch by a bunch, because it's very fast. Let's see, what else can we do? We can change the cost function. So like here, I'm minimizing the added volume every time I take off a face, but I can also minimize the surface area. In this example, it doesn't change a ton, or the average width of the shape changes like a little bit. If we reset to the beginning and just like go to the target, you can see it's pretty fast. It's like, I think on all the examples it's like less than a second or a lot less than a second. That's online, you can play with it. Cool, let me show a few more results. So here I'm gonna compare to other variants of convex hull simplification that work in a manner similar to mesh simplification. So one idea I found on like an old blog article is this idea to like just run QSlim on your original shape or on the convex hull of your shape. Just like let it not make a convex hull, and then afterwards use those faces and like push them out just enough so that it's making a proper containing shape. This works okay sometimes, but tends to add a lot of volume. This is that algorithm I was talking about before. This works by collapsing edges one by one, just like mesh simplification, but every time it collapses the edge, it has to either keep the volume the same or increase the volume. So it can only really grow outward. This worked well for their use case, which was not 3D geometry, but doesn't work well if the input is 3D geometry. And I think like maybe the key insight here is that like growing outward, that you should do in the half space representation, and growing inward is a better choice for this vertex representation. This scared me during the paper because this turned out to work a lot better than I thought it would. This is just like, make your dual hull, like the exact full dual hull, and just run QSlim there. And like don't worry about like volume change or anything. Just use their like appearance minimizing metric, and then just like convert it back to the primal space afterward. And the first couple of examples I did was like working really, really well, and I was like, oh shoot, like that's like too simple to publish. But like over a lot of examples, you can start to see that this doesn't always work, and it's because it's using the wrong metric. It's like trying to make a shape that looks like, in terms of rendering the initial shape, not something that's trying to minimize the volume, which is usually what you want, or some other geometric quantity. So this is our simplified version of the teapot's hull. Here's another example I'm going to compare to a different set of algorithms this time. This was an idea where the idea is you take all the hulls, or all the normals of the convex hull, and then just try to like do clustering based on the normals, like sort of treating the normals as Euclidean space and doing clustering. This is very counterintuitive. It actually does like pretty much the opposite of what you want and gives you pretty bad simplifications of hulls. And here I'm using a metric that's like not the one that I'm optimizing as sort of a third-party validation, maybe. This algorithm works like on the other end. So instead of like removing faces, it tries to slowly add faces. So it starts with just like a tetrahedron and tries to like add faces. This works pretty well once you start adding a bunch of faces, but when it's really small, you're really biased by the first few faces that you pick, and there's not a cheap way to pick the volume minimizing tetrahedron of an input shape. This is the algorithm that scared me. Again, here it works particularly badly. And then I really like this result. It felt like exactly what I would want in terms of a like six-sided shape, which is a really low number of faces for containing this motorcycle. Here's another example showing that clustering not working super well. This is like pathological to hurt that algorithm. So it's like putting too few faces in the dense area and too many faces in the coarse area, whereas our simplification does what we expect. Here's a plot over that 133 model data set. We're showing volume increase across a bunch of different algorithms. This was like simplifying them all down to, I think, 18 faces. And we have similar for surface area. I'm going to skip a couple examples because we're running low on time. Where should we jump to? Let's jump to, oh, this took me so long to render, I have to show it. This is just like using the convex hulls in a rigid body simulator, which sometimes people do if they run a really cheap simulator. You just like literally use the convex hull instead of the shape as the proxy for simulation, and it looks pretty good. This is combining it with approximate convex hull decomposition. So most of these methods work by selecting subsets of the faces in a hierarchy. And then most of the like libraries have some attempt to simplify them, but they don't work particularly well. And they allow the shape to leak through. So here you're seeing, if we use the VHCAD, or this method for convex hull decomposition to simplify it, it doesn't look so good. If we just plug in ours as a drop-in replacement, it still contains the shape with very little volume add. I'm going to skip one more. Let's skip over that. It's just another one. OK, so here is switching the metric. So far, I've shown volume minimization for most of the examples. We can also do surface area minimization. For a large number of faces, it doesn't really change too much. But we can see that like big spike went away, which was like very painful for area, but not so painful for volume. One interesting thing is that each of these quantities kind of corresponds to an application domain. So volume, minimizing volume, it corresponds to like minimizing the false positives that you would get with intersecting a point probe. That's just like what volume is, right? Like adding up points. Surface area corresponds to lines or rays. So for like ray casting, that would be a good choice. And mean width is what you get if you want to minimize false positive with respect to hitting a plane. So if you're doing like a lot of ground plane intersections, then mean width or average caliper diameter is what to minimize. This is a picture showing that. Look at the paper, I guess. Yeah, I'm going to skip that one. This was an interesting, so we can also just run our volume minimization or area minimization in the primal space, and we get something that's as tight as possible to the convex hull, but on the inside of the shape, which I think has debatable use cases, but like maybe you would want to do this in a scenario where like false positives are just like really not okay. Like you didn't want to have your football like floating on the ground. It was better to have it intersecting with the ground. Okay, limitations and future work. The theory for this was like pretty well developed in the like math and theory literature. I cite a bunch of those papers in the paper itself. One thing that is like an annoying problem is you take like a canonical shape like a icosahedron and you simplify it. There's a lot of symmetries. Like a lot of the plane removals look exactly the same. And they even look the same in places that end up like breaking the symmetry of the final shape. So this is typically what we get if we like randomly rotate the icosahedron, which is like not very good for the minimal four-sided shape. Sometimes we get this thing, which is the optimal rhombohedron. The sad thing is that like that greedy path, once it gets here, it will never get here. So it's like, once it makes a decision early on to get to that will arise in this shape, it'll never make it to the optimal tetrahedron. So like maybe some future work here is to like find better paths than the one greedy path, which you could do with beam search. Maybe there's some way to like polish these faces. This is like surprisingly difficult. We're doing like a subset selection problem, but maybe there's a face that doesn't exist in the original faces that would be better to choose. And then there's other ways to define hulls that aren't polyhedral. Yeah, let's be done. Thank you for your attention. My funding agencies, friends that I talked to about this, and the people that made the models. Happy to answer questions if there's time.
Questions? Questions? I have a question.
Sure.
In the primal convex hull and the dual convex hull, when you are doing the volume calculation, because you care about volume loss or volume increase, is there a monotonic correlation between the volume increase or decrease on these two sides?
Oh, yeah. So, yeah, I looked into this briefly. So I want to put an asterisk on whether what I'm about to say is true. It is not a simple proportional relationship. Like it would be kind of cool if I could just compute volume in the dual space and just say like primal volume is like 1 over that or something like that. I believe my conclusion was it's like annoyingly dependent on like what point you choose to be the origin in the dual space, and then it's like non-trivially related to that. But like basically, I convinced myself, no, I have to measure it in the primal space.
I see.
One kind of funny thing that came up in the reviews is that like it does seem that like everything should just stay convex between primal and dual, but in fact that little cap thing is convex only in the primal space. It's potentially and almost always non-convex in the dual space. If you kind of think of it, it's like the little gap between two convex shapes, which will in general look like a little crescent thing.
Right. I'm going to reveal my ignorance. Right. I thought that in the dual space, right, the origin you choose is just the center of the sphere because you are considering the Gauss map.
Oh, it's not quite the Gauss map. You're kind of creating a dual convex hull around some point that's chosen in the primal shape, and that point just has to be somewhere inside of the convex hull. It can be anything. Like usually people choose the Chebyshev center, which is like in some sense the deepest point, but you don't have to use that point. You can use any point. And then that thing is like the origin in the dual space.
It's starting to feel like we need to have a conversation later.
Sure.
Any more questions? Olga.
Alex, so when you triangulate this gap, is it possible that you have several options that are convex?
Yeah, so like this was kind of like a nice thing that happened and wasn't a problem. So like one thing that can happen is you can, if you're willing to take input that's not in general position, which is a reasonable assumption because like most things, there's gonna be like many points that lie in the same plane. Then you can get into a situation where your initial dual hull is like perfectly fine, there's nothing degenerate, but then when you remove a vertex, you have like a bunch of points that lie on the same plane. Or even like a bunch of the neighbors lie on the same plane and other parts that like don't lie on the same plane. And then there's like, you have a choice of how you triangulate that planar part. And the kind of cool thing is it doesn't matter what triangulation you choose. Any of them will reveal the correct neighbors that you need for the following steps. So it's enough to just pick some triangulation, and then you'll get the right neighbors later. That was really fortunate because it meant
There are no non-flat situations that...
No, because it's like uniquely the convex. Like the only thing that you have to worry about is like things being coplanar because it's the convex hull in that case, yeah. But it means I can use a triangle mesh data structure and not a polygon mesh data structure, which was, I don't know, nice.
If you're doing this on an approximate convex decomposition, are there any clever things you can do at the places where the convex components meet? Because I bet like one of them might inform the neighboring one. Or something.
Yeah, I think that there could be. The only thing that I did was as a post process. So like I took their output without any simplification and I simplified their nodes basically, like their leaves. Some of the algorithms try to be smart about like putting a shared plane between the pieces so that they don't like waste too much overlap between them. You could, so I skipped over one thing that might be useful there. So in this hammer, this was like a constructed example, but it's like, oh, I really want that plane of the head of the hammer to be in the output. And since it's optimization based, I can just be like, yeah, make that infinite cost to remove. So you could do something like that, like you really want the shared walls between the pieces to be there, and then the algorithm would respect that. There might be more interesting things you could do if you were doing the convex decomposition knowing that you were going to run the simplification, but I didn't look into that.
Okay, we'll thank Alec again.
Thank you.